momentum theory. So we're jumping ahead a couple of chapters here, but maybe it'd be interesting to come back to this after you've studied chapter 7 on angular momentum. But when your wavelength is large, it works out that your L is actually 0, and that corresponds to so-called S waves, S for spherical, because when you solve the full Schrodinger equation, when angular momentum is involved, and the Schrodinger equation is not only a function of the radius, but also the two polar angles, theta and phi, then in certain circumstances, sometimes you'll get a symmetric wave function, but other times the wave function, the solution to your Schrodinger equation, depends on the polar angles, depends on theta and phi. So you get these sort of loops, sort of like wings coming out that vary in size depending on your theta and phi. So so when the angular momentum, when L is 0, you get S waves, meaning spherical waves. Right? You have this spherical, U, the wave function, is spherically symmetric for those cases. Well, you need to do chapter 7 to see that's the case. So it's only when L is 0, with these large wavelengths, that you get significant scattering, and we can now make that quasi-plausible using a sort of semi-classical type reasoning, correspondence principle type reasoning. It's the following. Here's your target, okay, and here's your particle coming in with momentum h bar k, right? K, the wave number, 2 pi over the de Broglie wavelength, 2 pi over lambda, okay, and let the this line here is like, if your particle came along this line, it would be a head-on collision with the target, dead center, bullseye. But let's say the target's at a distance b here from this line. This vertical distance between the particle and this line is b, little b, and that little b is called the impact parameter. It's a measure of the closeness. It's this distance from its position to this line, which is like the bullseye line, if you like, called little beta, the impact parameter. Now, classically, as that little beta gets smaller and smaller, the deflection angle, theta here, say it flies off like that, and that angle theta between the horizontal and the direction that it flies off, deflection angle, if you like, that theta, as little b here gets smaller, this deflection angle theta will increase. Right? So as this gets smaller, this gets bigger. That seems reasonable. Now let's assume that that this potential drops off with distance, and so effectively, let's say when little b here becomes large enough, there's no deflection. Right? There's no scattering. It just goes straight through. It's not. This particle is not feeling anything from this potential. Let's say, and so let's say the distance of interaction, its range, if you like, of this scattering particle, call that R0, right? R0. So if this impact parameter here is larger than that, this incoming particle will not feel anything, right? It won't deflect. Okay. So so in that case, there's no scattering. So we're interested in scattering. We want to know what's happening. So in other words, we're restricting our attention to when this impact parameter here, this little b here, is small enough. In other words, in terms of angular momentum, now think classically, think classical mechanics. What is angular momentum? how you define it? Well, say I've got a weight here on a string, and you know, I'm turning the weight. So imagine this pen here, that's the string, and the weight's attached to the top, and so it's doing this. Now, relative to the center here, where I'm holding the string, the angular momentum of that mass m going at velocity v, or let's say speed v, is the momentum, so mv times that distance, call it r. Okay, so the angular momentum of that mass here at the tip of the string, end of the string, will be mvr. Okay. Now, in this context, the angular momentum relative, well, when it gets close, if you like, will be mvb, and the momentum is, it's a de Broglie particle, has a particle wavelength, whatever that means. Okay, so h bar k, that's the momentum of the particle, right? And b here, that's your impact parameter, that's your distance. So this here is an angular momentum. So we're interested in the case where your h bar k little b, that angular momentum, is less than h bar k r0. Remember this r0 here, that's the distance beyond which the interaction between the target and this incoming particle is 0. Right? So we're interested in when the angular momentum of this incoming particle is less than h bar k r0. Right? That's like the cutoff angular momentum, if you like. All right. Now, it really would pay to come back to this after you've done chapter 7. But anyway, from chapter 7, the quantized angular momenta that are allowed take this form. So this is sort of a bit of a summary of the results of chapter 7. Is just h bar k square root of L into L plus 1 here. These are the allowed angular momenta of in quantum mechanics. And these L's here are integers, right? So so that means that this so the allowed angular momenta, so we can instead of this h bar k little b, we can plug in this formula, right? So this is the angular momentum of the incoming particle. And from the theory of angular momentum, we know those values are quantized. The angular momentum, menta, plural, are quantized, and they take this value. Okay, so that means this value here has to be less than h bar k r naught. I've run out of board for this session, but I can give you the qualitative conclusion. If you plug in values here that are realistic, for real world, like this R0 here tends to be a few femtometers, 10 to the minus 15 of a meters. You can figure out, for reasonable values of little k, and given the energy, whatever, Planck's constant. So you end up deducing that this L has to be 0. Okay? And if L is 0, your Schrödinger wave function is spherical. And you'll learn why that is from chapter 7 on angular momentum. But when L, this little L here, when it's 0, your wave function is spherical. It's an S wave. Okay. So when L's 0, you get S waves, and you only get you'll only get significant scattering with the S waves, and we can use that knowledge later on, which will help us find a formula for your deltas. And we need to know what these deltas are, the phase changes, to know what F is, right? So it's a multi-step chain of logic, right? And if we know what f is, you know, the scattering amplitude, f of theta, then we have knowledge about how everything scatters. That's what we're ultimately after. Okay, so okay, I'll stop there.